Okay, I'm Wylie. I do process development at Biperliminate. Opening slide actually is relevant. This is one of the very first experiments we did with the technology. This is a medical dye. That's the feature of most of the attempts at high concentration. This is a medical dye. It's used for testing your kidneys, methylene blue. And even though this is the first generation of the technology, we're now on number 3. We were easily able to destroy 25 ppm for under $1 per cubic meter. Obviously, that would be tiny pennies or fractions of a penny for this kind of volume. So I'm going to talk about the issues that we face. Most of you are aware that there are microtoxins in the environment. I don't know if all of you are aware of how serious it is. It is actually a growing epidemic of microtoxins, including hormones and certainly drugs. By the way, in London now, the city of London, England, they're using cocaine in the wastewater to monitor cocaine usage in the city of London. They found cocaine in shellfish in northern England, in Seattle. It's all around us. So what is the particular chain that is most of a concern? Obviously, there's food in general, but people think that when it goes into the body, it's changed forever. That is not true. The vast majority of drugs, hormones, pharmaceuticals, and industrial chemicals that you ingest get eliminated in your urine, and they go into the wastewater stream. Now, they're relatively low levels, but that doesn't mean they're low effect. They're very, very significant. For example, in the last 60 years, male fertility has dropped 50% worldwide. In North America, the average girl goes through puberty 4 years earlier than 50 years ago. These are big, big changes in our lives. Breast cancer is a huge issue for women. Female fertility is dropping as well. These are mostly due to our food, to be fair, but after all, the animals are drinking water that is also contaminated. There's huge amounts of hormones being released into our wastewater, and I mean huge in relative terms, relative to their effectiveness, not in terms of the concentrations we're used to dealing with. So obviously, our traditional secondary biological treatment isn't as effective as it needs to be. Now, one of the things that people have grown accustomed to is that the pharmaceuticals and so on are sequestered into the bacteria as they die and settle at the bottom. So you can get removal rates as high as 80%, even though sometimes 20% is very, very high for these very effective compounds. However, they're not destroyed. So when those biosolids, as they're called, are sent to a landfill, lo and behold, it rains, the leachate contains it, it goes back out in the environment, or it's put on our fields and it ends up in our food. So the destruction of these compounds is what we should be seeking, not simply the diversion from a waste stream. And of course, I live in the Lower Mainland, huge quantities are going into the Fraser River. The only reason we can get away with it is there's 5 million tons a second or some huge volume going by. So that's some of the challenges we face. Of course, there's industrial waste as well. And so ironically, the biggest challenge is not a physical challenge, it's a mental challenge. And that is that everybody, to a certain extent, and certainly the large organizations, have a tokenism attitude to pollution. They're not seeking to solve the problem. They're seeking to be seen to solve the problem. That's a different thing. How do we change the culture so that people don't apply feel-good solutions that don't solve problems? How do we focus on the science? So greenwashing is a very big problem. And I'm here today to say that there's solutions, but the attitude has to change. The culture has to change. The biggest issue with these chemicals is that they're estrogenic. 90% plus of the hormonally active compounds mimic estrogen in the body, and they affect men and women, of course. Huge amounts of it. And so if we have an oxidation process, what is an advanced oxidation process? Well, everybody knows oxidation to a certain extent. Every time they drive their car, they put gasoline in, and after a while it disappears, becomes carbon dioxide because it reacts with oxygen in the air. That's a regular oxidation process. An advanced oxidation is where we generate something that's far more reactive than molecular oxygen. We call them free radicals. Now, free radicals are a big problem in our body, and the body deals with it quite well, usually. But free radicals in an advanced oxidation are an enormous asset. They dramatically enhance the reaction rate. And so that means that we can drop the price of treating our waste if we generate enough free radicals, and we do in Biperliminate and some of the other processes that we compete with. So the market is huge, far larger than I'd originally anticipated when I started this project. There are huge applications of this technology. Obviously, I've mentioned drugs and hormones, but landfills as well. Sometimes the drugs and hormones end up there. And of course, industrial sites. You'd be surprised, even in a country as sparsely populated as Canada, there's hundreds of old industrial sites. I've been to some of them. They're quite terrifying that underneath the ground, there's coal tar, refinery waste, you name it, all around us, but we don't know about them. But they're there, polluting our water and our food. And of course, the tar sands, oil sands. I shouldn't say tar, I apologize. Okay, so one more thing, I'll use the word refractory a lot. Refractory just means a very stubborn compound in general, but for our purposes, we're going to talk about refractories in terms of chemicals that are not treated with traditional biological or secondary treatment, okay? So there's a good reason why Biperliminate, and to a certain extent others, but not as much, other AOPs go after the most toxic compounds. And you're going to see a lot of these ring structures. I'm going to show you some of the chemical structures of the compounds that we destroy. This is just a sample, just illustrative. So those rings are huge sources of electrons. And so those electrons are very attractive to the free radicals. So this is again an enumeration of the issue of the problems with hormones. EE2 is obviously, there's no one particular drug or pharmaceutical that is the biggest problem. But unfortunately, they use a synthetic estrogen called ethylene estradiol, or EE2, in the birth control pill. And unfortunately, it's also 90% converted at least into the urine. So if you think about it, all of those prescriptions worldwide, and it's 30,000 kilograms a year, 90% of it is ending up in the wastewater. And what fraction of that actually gets treated could be as low as 10 to 20% in traditional treatment. So when you do the math, how much estrogen does that work out to? That works out to, if you were to give it to men, more than 100 times enough to convert men to the hormonal level of women. Sounds like a good thing for women maybe, but no, it isn't. So there's lots of other chemicals other than estrogen. Bisphenol, you may have heard of, BPA in plastics. We've just gotten rid of it mostly from baby bottles. 4 million tons a year. Thank God it is not as estrogenically active as EE2, which is designed to be estrogenically active. Cows, pregnant cows, there's 1 billion cows on the earth. 1 billion. Think of that. That means more mass of cows than people. And of those, roughly 40% are pregnant at any time. And a pregnant cow generates 100 milligrams of estrogen, fortunately not E2, every day. And that's a gigantic flow into our rivers. So unfortunately, if you go downstream of a dairy farm, you'll see in the streams, you'll see huge amounts of estrogen, and there's some very bright people who've been doing that. So although I like my cheese, I'm well aware that there's a lot of estrogen in it. It's not the number one source of endocrine disruptors, to be fair, to the dairy industry. Okay, so AOPs are these processes that are used to generate these radicals that oxidize or destroy many of the toxins we care about, especially the ones with that ring, that aromatic ring. Okay, so Some of the well-established competing technologies that are used mostly in drinking water, not wastewater, are ozone. That's well known. Ozone is used in a lot of areas very effectively. It's an extremely good technology for disinfection, very competitive with chlorine. I could argue it's better than chlorine in some cases. It's also used for bleaching. However, ozone has a lot of drawbacks. Uses 20,000 volts to generate it. So the capital cost of the units is quite high. Ozone is also extremely toxic. It literally will burn your lungs out. And it hates to be in water because it's not charged like sodium chloride. So you have to have a lot of air handling or outside. That's one of the possibilities. But the biggest problem for ozone for wastewater, it's not selective. That means it'll go after everything that's in the wastewater. If I asked you for a wastewater, would you think of wastewater as pure? I don't think so. The definition of wastewater is that it's not pure. That means there's a lot of stuff in wastewater that's not particularly problematic. Most of the wastewater we've dealt with is 90 to 95% mud. Sounds okay, right? But the 5% is toxic waste. Those are the stuff that we need to remove. So if you've got a non-selective process like ozone or UV peroxide, they're going to go after the mud at the same rate or faster than it goes after the toxic waste. So if you don't have selectivity, you do not have a process that goes after the stuff that you really care about, the toxins that are really causing the problem, I don't think you have an effective technology. So selectivity is the secret. So we've been working on that for over 2 years, very much as a team effort. So another problem with ozone, it simply doesn't have enough oxidizing power for aromatics. So many of the chemicals we need to deal with have this ring, which is very, very stable chemically. And so ozone does not do a good job. UV peroxide's better, but it's also not selective. And there's a lot of people that don't want to ship around 30% hydrogen peroxide. But it's also massively more costly than Biperliminate, 5 to 10 times. I'm going to show you some data on that in a little while. Also, because we're so low cost, our footprint is extremely tiny. Around about 1 to 2% of the equivalent flow rate of a biological reactor. But unfortunately, we're a very new technology and almost nobody knows about it, except you guys now. So you have a big advantage, right? I hope. Okay, I mentioned selectivity. So selectivity is all about going after the toxic, what's the time?
It's quarter to.
Thank you. Thank you. Good time. Okay, so this is, again, I use the word mud, humic acid. This is very close to our very first waste that we had from an Alberta wastewater. It had about, well, 1 ppm phenol was the worst case, and 100 ppm of mud. So you can drink mud. Pure mud is actually good for you, okay? Phenol definitely is not. A couple of parts per billion of phenol will kill you. It's also extremely water-soluble, very active, and relatively prevalent. And there are very few processes that destroy it, especially at low levels, like 1 part per million. Remember, 999 parts per million, 999 are water. So just burning it doesn't help you much, right? So if you have a standard non-selective process with a 1-to-1, this is very conservative because normally reactions go faster in high concentrations. You have to use quite a lot of oxidant, and you'll only, if you're lucky, mostly not lucky, you're going to have only 0.1 ppm of phenol. Most of the regulations are 1 part per billion, so we need a 1,000-fold reduction. That's very challenging. But if we have selectivity, which we do, this 40-to-1 number I've used, again, that means that the reaction rate of phenol is 40 times higher than the background. We're going to have only 40 ppm humic acid, and we'll get down below 10 parts per billion in phenol. And in reality, we have higher selectivity than that, despite the fact that higher concentrations are supposed to give higher rates. So that's the secret. With real wastewater, you have to have selectivity, and that's what we have with Biperliminate. Very straightforward process, extremely easy to integrate. I'm not going to give the details of our system or the chemistry. That's our IP. That's what we're keeping. We can't patent it. It's too expensive, and it would give it away. So we are keeping that to ourselves. But we're going to tell you what it does, how to integrate it, and we can manufacture these for any number of customers. Very straightforward. We mix the solution, oxidant mixture. It's a complicated mixture. There's more than one component. And this mixing process can sometimes give some default reaction. There's a very different reaction profile versus temperature. It tends to go faster if it's hot. However, this is where we generate the radicals. So this is non-radical oxidation. This is the radical oxidation. This is the AOP part. And it doesn't matter what the temperature is as long as the water's actually flowing. Okay, this is actually the first real data. This was from Alberta. You can't see it, but in the foreground over here, there was a big pond, frozen solid, 6 inches thick with ice. We had to smash through it to get access to the water. This was, we pulled it off the pickup truck. This was our pilot system at the time. And I'm going to give you again the structures of these compounds here, just so you can see the rings involved. So this particular set of data was generated from Caro, and this is two particular components of a landfill leachate. Again, mostly mud, but these are the small concentration of toxic chemicals that are problematic in the landfill leachate. That's when the rain comes down, the landfill's got some toxic components, and out goes the toxic components with the rain. That's the leachate. Okay, so xylenes is one of the components that's an industrial solvent, part of the BTEX class. It went from 39 parts per billion to 4 parts per billion. This was a very low dose, too low a dose actually, as it turned out. I would have done much better than that with a higher dose. And naphthalene, this is a coal tar derivative, and in 60 minutes we went from 13 parts per billion to 0.2. We could have done better than 0.2, but we don't know because that was the detection limit. Well below drinking water specifications for this polyaromatic hydrocarbon, PAH. This data is exactly the same water, it's just different compounds being displayed. Unfortunately, I changed the scale, so I don't want to be confusing here. This is parts per million of the total background. That's the total organic carbon. That's everything in the water that's not water. And this is in parts per billion of phenol, which was the one they were most worried about. So we went from 41 to 6 parts per billion. We'll do much better, and we did do much better in subsequent generations. This was, again, the first generation of the technology. The city was very impressed with this, but they did not purchase the technology. That's a political question. Okay, it's a long story, which we don't have time for. Okay, so this is a different pilot. This is another test. This is early 2018. This was still first generation technology. And this was, apologized. This is not. This was, I apologize. That's the next slide. This is me going into the lab and saying, okay, I wasn't satisfied with the phenol rate from Alberta. I'm going to do it better. So I used a more appropriate process. This is actually second generation process. And we use methylene blue. Okay, so you can see the destruction of phenol here, very low cost. Friendly guy there. This is the site, the industrial site in Vancouver. This is a Caro samples here, low concentration. And that was the data in the green line. So when we did it with a pre-soak, which was again this initial reaction, we were able to go from 980 to 0.2 detection limit in 10 minutes. We are very selective for PAHs. This was a brownfield site, not a leachate. This is, again, a municipal background, 69,000 parts per billion. During the process, in 60 minutes, you're up to 51,000. And PAH dropped from 3.2 parts per billion to slightly under 1 part per billion. So that's a huge selectivity because we should be much slower at that concentration. This is not a pilot, although we used our pilot system. This is one of the most tough compounds on the planet. It's called atrazine. It's a fungal drug, and nobody else has a process for it. We were easily able to destroy 98% in 30 minutes, less than $1 cost. This is PFOS. These are chemicals that are used in firefighting. PFOA is in your frying pan if you have Teflon, and nobody has a PFOA process. We only did 67% with our first try. So we went back in the lab and we generated a new pre-treatment process, less than 10 cents a cubic meter, and so we used foam because that's cheap and quick. So this is 2 ppm. This is the foam from 2 ppm PFOA. 10 ppm is that high. So after the pre-treatment, that's what a 10 ppm solution looked like. So I can't tell you exactly what the concentration is, but it's a heck of a lot lower than 2 ppm. We also do mine water. Cyanide is used for gold mining. This poor guy, the fish is dead. I guess the cyanide killed it. But this is the destruction of cyanide in the lab from 14 parts per million to about 1 part per billion in 30 minutes. But we converted it to ammonia, and then the ammonia itself was converted to nitrate. So we destroy ammonia as well, which isn't considered an organic. Costs for Biperliminate in the range, this is a typical capital cost measure, dollars per cubic meter per day. Somewhere between 50 and realistically 100, but I put 200 just to be conservative for Biperliminate. This is the cheapest you're going to get for traditional biological treatment, which doesn't touch these refractories. And here's our best competing technology, 10 times more expensive. So here's an Here's an example of integration. This is the second to last slide, in case you're worried. This is an example of the process being integrated. This can be used downstream of a nanofilter. Nanofilter is just a membrane that separates out molecules, and depending on their molecular weight, the small molecules will pass through. Those tend to be non-polluting. The big toxic molecules are rejected to the Biperliminate, which destroys them. And if you're really worried, you can put activated carbon afterwards, and you'll get almost drinking water quality out there. Okay? So that's one of the ways it can be integrated. There are many other ways, but I wanted to show you, by the way, in addition to this integrating it well with an existing secondary treatment, even for municipal, but it can also be industrial, this is a way to make the process even less expensive. So, to finish up, again, I'm challenging you. How do we change this culture? These chemicals are affecting our health right now. And obviously the biosphere as well. There's a lot of female fish out there that used to be male fish. Not a good thing. How do we change that culture? So these are the results I've shown. How do we change that culture? I'm hoping this can be a component of it, but I'd love to hear your ideas. So we've done pilot testing on several dozen compounds. They're very efficiently destroyed, especially if they have that ring, the aromatic carbon. The wastes are converted to vinegar, carbonate ion, beer, and food. We've even been able to destroy the perfluorinated compounds used in firefighting and on frying pans. Less than 40 cents a cubic meter for 10 ppm. Nobody's got a process anywhere near that. Our selectivity is the secret. We're selective for these compounds. We're anywhere between 5 and 20 times cheaper than the best competing AOP. We're completely safe, very environmentally friendly. Our footprint's tiny. A system the size of this can handle hundreds of cubic meters a day. I don't expect you to believe me, but I do expect you to challenge me with some water and make me prove my claims. Please do. We're the lowest cost, readily scalable, lowest footprint, and most effective AOP known as far as I can tell. I've been looking, and we are cheaper than even granular activated carbon and digging up and relocating it, and we actually destroy it or convert it to something harmless. So I'll have to ask you, given this and given what you know, how do we, so when you put up your hand, you can ask a question, of course, but please give me your opinion. How do we change the culture that is destroying the environment in a very subtle way? Thank you.